Um, Hello, everyone. Thank you for being here. I will be presenting mostly from the chair, as most of the audio equipment doesn't work, so apologies for that. And today we will be discussing the privacy-preserving systems using FAG-friendly ciphers, as made by me and Bitul and Dilara. So let's go straight into it. So first of all, we have a lot of things to do in this presentation, but let's first reintroduce everything for everyone so that there's no information not already known. So first we'll go over a general overview of just simple ciphers and asymmetric encryption, symmetric encryption, block ciphers. What are these things? Just for a simple and quick reintroduction. We'll discuss the privacy-preserving system and the needs to have them in this emerging landscape through data and online. We will be mainly and mostly discussing Transciphering, which is a form of getting FAG, which is fully homomorphic encryption, to work with larger data sets as the transfer size is big, but we'll get to that. And the goal of this thesis, or this presentation, not yet really, is to see which FAG-friendly block ciphers are really efficient and are good for this transfer capacity, and to have an experimental and numerical results that get from this. Okay, so first of all, very simple, cryptography. We will mostly be discussing the symmetric and asymmetric ciphers, mainly the block cipher within this. But you already know this. The asymmetric one has the property that there's a cloud where we can store our shared key, or public key as it is known, but we also have a secret key, which is only known by the person generating the encryption, so that everyone can encrypt whatever data they have, but nobody can decrypt it except the owner of these keys. We also have the symmetric one, which is well, I mean, it's one key, so only the owner of the key generation algorithm knows how to encrypt and decrypt it. And that's it. Okay, so let's jump into what a block cipher is. It's a part of the symmetric key family. And the way that it works is it creates a long string of keys and encrypts per block these values as a symmetric key encryption would work. So we have a fixed size blocks and we encrypt them symmetrically. Okay, so what is fully homomorphic encryption? This is the concept where we have homomorphic operations while in the encrypted space. So when we encrypt something, we want to still be able to do operations with them. So addition and multiplication mainly, but maybe also other operations. And fully homomorphic encryption, or FAG as it's known, can do this through the use of rings. And there are a few key properties of these fully homomorphic encryption, such as noise management, where we create noise within the encryption, so that it's very difficult to pair input to output. So even very small changes in the input create very big changes in the output. But this means that we lose some bits or some available space and encryption space to this entropy, which means that we need bootstrapping. What is bootstrapping? Well, it's just redoing the whole encryption algorithm so that we decrypt it and then re-encrypt it to kind of get back some of the noise bits. And we also have leveled FAG, which is a concept where if we don't want to do bootstrapping, we just create the whole encryption algorithm a priori with a known depth limit of non-linear operation, so that's the AND or multiplication, so that whenever we stay within this limit, we don't need to bootstrap again. Okay, so what are FAG-friendly block cipher? Well, basically it's just a block cipher where we can encrypt the data, and the encrypted version in symmetric cipher can still be operated on with the FAG algorithm. So there is a big opposition with normal of most of the block ciphers, which is that most block ciphers prefer a low latency optimization. So that means that it's very, very fast. And in most cases, this is already hardware implemented instead of only software implemented. Excuse me. Meanwhile, the FAG-friendly block cipher have more of a focus of the nonlinear operations. Because as I said, the leveled FAG, it requires that there is a priori known level of the amount of non-linear operations. So we want to reduce them as much as possible, so no bits of entropy go towards the symmetric encryption or decryption, instead of going to what we actually want to achieve. This means various things. So there's a lot of people who have come up with very smart FAG-friendly block ciphers, as you can see here. And the main purpose of this paper will be to evaluate most of them or some of them and to see which ones are eligible or most efficient for huge data transfers in a privacy-preserving system. Okay, so what is this transciphering that I've spoken of? This is the concept where we encrypt the data with a FAG-friendly block cipher, and then use this FAG encryption, decryption, and evaluation operations to do secure computation. That means we first need to encrypt the data with this FAG-friendly block cipher. Then we encrypt this symmetric key that we got from the block cipher encryption algorithm with the FAG encryption. Then we can transfer the amount of data, which means that it stays, relatively small. It's just as big as the normal block cipher operation, instead of growing very big with the FAG encryption. And then at the server side, which we will get to in a bit, we will transform the ciphertext into an FAG-compatible format through decrypting the block encrypted data towards FAG encrypted data using the encrypted symmetric key, which is a very difficult sentence to get out. And then we can use it as we always did, because from that point on, it's the same as FAG encrypted data, and then we will see what we can do with that with regards to a privacy-preserving system. So the advantage of this is the transfer size stays relatively small. It's just as big as the normal symmetric block cipher encryption, and it maintains the properties that we want from fully homomorphic encryption, so that we can do operations with the encrypted data at a site that's not owned by the people who own the original data, and so that nobody can look into what is the original data. Okay, so let's go into how transciphering works. As I said, this is just a simple version of how we could encode it. With the transciphering in algorithmic form, which is a bit more complicated than it is with the non-transciphering form, where we just do the encode data with only FAG encryption, and the processing data is only FAG evaluation. But it appears that slide has been removed from this presentation, for which I do my apologies. So what is this privacy-preserving system? The goal of the system is that we have multiple parties who are interested in this data or who own the data, and we want to do a certain algorithm to explore how much of this data we can get. So we have a few core components that we need to keep in mind, which is input privacy, namely the people who own the original data don't want that original data to be known. We have output privacy. If someone wants to request a certain function of data, but they don't have ownership of this data, they don't want the result to be known by anyone else. We want to have anonymity, which meaning that nobody knows who each other exactly is, which is more difficult to do. And access control, which means that, well, if I'm owner of some data, I want to still retain control over who gets what of that data. And I say data arbitrarily, but it just means whatever we're talking about. Okay. So then there's also two threat models, meaning a semi-honest model or a malicious model, meaning, well, everyone works as the system is designed, or somebody tries to gather as much data or be nefarious with what they have access to. But for this, we will assume a semi-honest model, but this will be explored in a bit. Okay. So, use cases of this, because it's very interesting. Well, I mean, medical data is first and foremost. Nobody wants to have known what their medical files are, what their properties are. There is a lot of GDPR, I think it's GDPR, rules which prohibit hospitals from sharing this data, or researchers just taking raw data and being able to connect it to a specific person. Within big data processing, so financial data, IoT devices, meaning that everyone has a bit of available data that they want to process, but there's not one single entity who owns all of it, and maybe they don't want each other to know what they have themselves. And also secure multi-party computation, so that means that everyone has their own sets of data pools, and they want to achieve some aggregated results. So that means, for example, the average of a price or how much is actually shipped of a specific product, but nobody wants their own data sets to be discovered by the others. And as this technology evolves, we probably will get a lot of different use cases that we haven't thought of. Okay, so how does it actually work? Well, first of all, we have 3 different components. We have data customers, the people who want some specific result. We have the data owners, so people who have the data that they want a result of. And we have an aggregator or server, so someone who processes who can speak what's and like a singular entity, as you can see in the middle. So he gets all the data and he distributes the result, but there's no way that the data owners can actually talk to the data customers directly. So first of all, the data customers generate the keys and they retain the private key, but they distribute the public key towards a cloud or an entity that can distribute it amongst everyone. Then the data owners, if they choose to participate, they can encrypt their own data, they can transfer the data, then the server will do the computations necessary for a specific function, and then they transfer the result, and then only the data customer can actually decrypt the result, and they get a nice evaluation. Okay, so again, data access is a very important part of this. So I want to quickly stand and look at, I want to quickly take a moment to look at who owns what data. And the most important part of this is that, as you can you see the mouse? Yeah. As you can see, the data itself is only known by the data owner themselves. In both cases, because we have the transciphering and no transciphering. This is the most important part. And also, the decryption of the result of whatever function we choose is only known by the data customer. And again, with transciphering, that remains the same. The only thing that actually changes in regards with the transciphering is in the transfer process and the special way it needs to be transferred and the special way it needs to be accepted. Okay, so let's discuss these input privacies and so on. As we can see, whenever the server, goes along with our system, most of the things will be as it should. But there are a few things that can happen, but because we don't want to deal with them, we ignore them, or we say specific requirements. For example, we don't want the data owner to server transfer to be listened to from the data customer, because if they have the private key, they can actually decrypt the original data. But because the server doesn't have the private key, the server can't decrypt the original data. It can only process it towards the result. And I do want to apologize because it seems that my slides are messed up in order a bit, so I can't show you what I actually want to show you. Which means that we have 2 different systems in place, namely one where the first one, version 1, where we just send all of the data towards the server, and the second one we have a choice factor, which means that every data owner can choose who they send their data towards. So they can choose what data they send or what data they send to which data customer. Okay, so let's go through these 2 systems. And as I've ascertained it, both do the most important part, namely the input and output privacy. So nobody knows what went into the system and only one person knows what went out of the system. And their anonymity is different because for one, everyone is forced to send their data. But for the second, they can choose whether they send their data. So they can choose to either send their encrypted data or they send just an acknowledgement message or something. And access control is also something very important. Namely, we want the data owner to be able to guide where their data goes or to whom their data goes. And for the first one, that's just absent because they have to share it. And for the second one, because they can choose not to participate, that's a good bit more. It's better. Apologies. Okay, so let's look at some results. First of all, we want to discuss quickly what libraries we used, and because of the main FAG encryption algorithms being PGV, BFV, or CKKS, as I understand it, we want to have a few of them. And as you can see, OpenFAG is one of the ones that's the simplest to work with in this case. It also has a neat package into Python for when we want to have easy comparisons. But there's also some other ones like HElib or Seal that we want to use to have different results, and it's a fairly bit more worked on and faster. Okay, so we want to implement, in terms of benchmarking, what we actually want to get is to implement this privacy-preserving system to see how many transfers are there, how big does the data grow with transciphering, without transciphering, analyze this performance, and just see whatever we can get out of it in terms of benchmarking. And we also want to see specifically, and we do this mostly through the framework of hybrid homomorphic encryption. We want to exactly measure how much these different FAG-friendly block ciphers grow in size under which FAG encryption algorithm. So let's look at that. First of all, I think you can clearly see the images. So first of all, and I do want to remind, this is a log-log plot, meaning it's log scaled in both axes. We have different results for different plain text moduli, meaning that for some operation, and in this case, to have a simple, to have a simple testing setup, we just add and multiply every input of data. So for some evaluations, this grows beyond the modulus, which means that we get errors or we don't get the same output as is expected, as we can redo the input to output evaluation algorithm function and see if it's actually the right one or if it's returning garbage. So whenever you see no plot, that actually means from that point on that it stops really working because the data grows beyond this modulus, which means that it's garbage in terms of what it can actually, compute. Okay, but as we expected, the more data owners that we have, the more time we're spent on processing this data and transferring this data, and it grows linearly. And again, this is log-log plot. And when we change the amount of DCs, we get a very, very linear acceleration, meaning that we just have to redo the whole system. So that means that it's comparative to just a for loop on top of the system. But these are some interesting results for different plain text moduli. And then we also look at the timing that it takes if we have different data points. So these are done with just a data point, so it's not really efficient to use transciphering instead of purely FAG because it doesn't grow that much. But here we can change that and we can go with much bigger amounts of data. And we can see that even for some cases, it still fails if we have a very little modulus. But most of the cases, it's really, really quick in this privacy-preserving system. Okay, so let's take a look at the comparison of different FAG-friendly block ciphers themselves. And we're going to start off on Pasta, which was made with these use cases in mind. So we see, again, different plain text modulus, which means that we have bigger and bigger amount of data that we want to encrypt, which means that we have less space available to use towards noise, and we get, we get less entropy to work with. So we need to be careful with how big it grows. As you can see, this entropy, so the noise amount of the available noise bits drops as we do go through the process. So at first we have the encryption themselves, so this happens at the user side. Then we get the encryption that happens, not the encryption, the evaluation that happens at the server side, which takes quite a lot longer, and then we still need to decrypt it and actually do the computation. And both these cases are combined in the last column. And we see at the end we have a lot less noise bits remaining than we did in the beginning. I hope this is clear for the most part. The most interesting result of this is the amount of RAM usage, which means that it's the amount of data that needs to be available at the server side. At the client side, it's actually a lot less, but it was difficult to measure this, so I haven't yet. But on the server side, depending on the FAG-friendly block cipher or the FAG encryption, it takes a whole lot of RAM, which means that for most of these results, as you can see, we don't have any results yet, as I can't handle this amount of RAM usage. Okay, so as per conclusion, as far as this paper goes, it is expected to yield some results that confirm that FAG-friendly block cipher reduce the size of the transmission of data. We also noticed that PASTA is a perfect FAG-friendly block cipher at this point to do our privacy-preserving system, but a lot more testing is required. In our future work, this is exactly what we will do. So we will test a whole bunch of different FAG-friendly block ciphers and hopefully some FAG systems to benchmark this. Thank you very much for your time, and are there any questions?